Record. There we go. So we've got to finish chapter 4, and remember what's happening with these is we're essentially going to finish chapter 4, so 4, 3, 4, 4, and then we're going to go into chapters 5 and 6. So 4, 3, and 4, 4 is not going to be on your third exam. This content will be on your final, but I'm going to focus on the third exam being just integrals, which is chapters 5 and 6. So you don't have to worry about remembering derivative stuff as well as the integral stuff for your next exam. But we do have to finish it for the sake of finishing it. So remember, chapter 4 was all about finding maxes and mins. So we talked about finding local extrema, and now we have to find a different kind of extrema. It's a very similar process, so we're still going to be finding derivatives, finding critical points, so setting derivatives equal to 0 and all that jazz. But it's just a slightly different process for the end of it. So here we go. So the techniques for finding maximum and minimum values for a function make up a field of mathematics called optimization. And that's mainly because a lot of times you are really looking to optimize something. You're looking for the largest area or the largest profit or the smallest cost. You're trying to make an optimal situation. And that's kind of what we're going to look at here. We're not just going to look at local maxes and mins, but we're going to look at these things called global maxes and mins. So for a function f has a global maximum at p. Let me reshare my screen. No one's told me they can't see it, but just in case, let me reshare that really quick. So a global maximum at p, if f of p is greater than or equal to all values of f. And then f has a global minimum at p if f of p is less than or greater to. Oh, I am hearing myself. Or equal to all values of f. I'm still hearing myself. Oh, all the way over there. Okay, let's turn that down. There we go. Okay. So essentially the difference between a local max or a min and a global max or min is, well, I'll draw some pictures in a second, but essentially the global ones are the absolute highest and the absolute lowest values of the function. What's up, David?
Oh, my bad. I didn't mean to do it. Sorry.
Oh, fine. So they're saying, so local maxes and mins, you know, it was the maximum or the minimum and kind of that small interval around that point. But for here, we're looking for the ones that's like the actual highest value of the function and the actual lowest value of the function. Also, just like with local, although I didn't go back and forth as much, the word absolute is also used. So with local, they could also be called relative. Here, so with local and relative, I usually didn't go back and forth very often, but I definitely do sometimes slip into saying absolute instead of global. Your book uses global, pretty sure Wiley uses global, but if I say absolute max or min, it's the same thing, and I'll try to use global, but I'm a bit more used to saying absolute, so if I slip up, they mean the same thing. So we have a couple different situations where you can have global maxes and mins. We essentially have three cases. You can either be on a closed interval, an open interval, or kind of on the entire real line. So essentially the types of problems we're going to look at is sometimes we're just going to take like a piece of the function instead of the entire function, and we're just going to look for global maxes and mins over that piece. And then sometimes we're going to want to consider the actual full function. So the first thing we're going to look at is global maxes and mins of a continuous function on an interval, including endpoints. So a closed interval. So what you're going to do there is you're going to
global.
Sorry?
Yay, we took a test on that. That was the last.
Accidental unmute. So the first thing you're going to do is find out critical points. So it starts off very similar to what we were already looking at. So we start off the same way as with local. What we're going to do then is we're going to plug all the critical points and the endpoints into the original function. And you're going to compare y values. So with local maxes and mins, we were often plugging back into derivatives. Here we want to plug back into the original function. And the point of that is we want to know which one's actually higher than the others. So we need to compare their y values. So I want to draw two pictures of kind of two different situations we can have here. So say, I'm splitting it off and just looking at the function between a and b. I'll do that in different colors so we can kind of know, the difference. The function and where I'm kind of breaking it up. And so say I have a function that looks like, so I want there and maybe about here, and then maybe we'll do whoosh, 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 there. So if you look at this thing that I just drew, if we were considering local maxes and mins, well, we kind of would have 3 of them. Maybe you could argue 4 of them, but I meant to try to only make 3 of them. So here, here, and here. I wasn't trying to make that last bit a max. So we have kind of those 3 local maxes and mins, 1 local max and 2 local mins. But notice how that first local min on the left, like the y value is lower than absolutely any other point on that function. That would make that a global min. So this one wouldn't just be, it would be a local min, but it would also be a global min. And then that local max in the middle, that value is higher, that y value is higher than any other value on that function. So that local max would also be a global max. So essentially, we could have global maxes and mins at local maxes and mins. But there's kind of a different situation as well. One of my screens is lagging. One of my screens is lagging. There we go. So, say we had a different function that looked like this. And there. And we go. Short. So we'd have a local min here and a local max here. But if we consider the y values of those local maxes and mins, neither of them is higher or lower than absolutely any other point on that, that graph. But if we look at the left endpoint, that y value is larger than the rest of the y values on the function. If we look at the right endpoint, that y value is lower than all the rest of the y values on that graph. So actually, when we're considering these closed endpoints, these closed intervals, we can have a global max or global min at the endpoint. So we would have a global max at that left endpoint and a global min at this right endpoint. So even though they wouldn't have been local maxes or mins of the function, well, maybe they were, maybe I cut them off very quickly, but usually they weren't. So even though these weren't going to be local maxes or mins, since we're kind of cutting the function off, they can end up being global maxes or mins. And you can also have a situation where one of them's at an endpoint and the other one's at a local. Like it doesn't have to be both at local maxes or mins at the endpoints. Like you can have one or the other as well. So that's why that process kind of works. We find all the critical points, find all the options for the local maxes or mins, and we compare the y values of the local maxes and mins with the y values of the endpoints and see which ones are the highest and the lowest values. So we're going to look at generically all of the situations first, and then we'll go into some examples. So that's when you have closed endpoints. You have a closed interval, you have a closed interval, so you include your endpoints. But we also have a situation where we might not include endpoints, and then another situation where we're working over the real line, or also possibly half of the real line, but I'll get to that in a second. So if we're on an open interval, so we'll write down the process and then I'll draw a picture again. So if we're on an open interval, so we're still breaking the function up into just a piece of it, but we're not actually including the endpoints, what you're going to do is you're going to follow the exact same process for closed interval, what we just talked about, and we'll see an example in a second. But the endpoints can't win, I like to say. That's not like an official way to say it, but I think it's an easy way to remember it. So let me draw the picture first and then try to explain what I mean by can't win. So say we're breaking this function up from A to B. And I'm making it dotted lines now to remind us that we can't include the endpoints here. And say my function looked something like, I don't know, this. So we'd have some local maxes and mins, 2 local mins, 1 local max. But if we started to consider global maxes and mins based off of the picture, that first local min would end up being the global min because that y value is lower than absolutely all other values on of that function. My screen's lagging again. Lag. There we go. So this local min would be the global min. But then if we were trying to consider a global max, what we'd like to say is we would like to say that this endpoint is the global max because its y value is larger than everything else on this function. But because it's an open interval and we don't actually include that point in the function, we actually don't have a global max here. So there would be no global max. And here's why. Well, after I write that, no global max. And let me try to explain a little bit more of why that's a thing, why there is no global max. So imagine I was like zooming in on that piece of the graph. So, here's the endpoint that we're splitting it up at. Here's the point that doesn't exist. And there's the function. So you could possibly say to me, well, what if, so let me give this a value so that it's easier to talk about. Let's say this was back at -1. Let's say we were breaking the back endpoint was at -1. So I would say that there's no global max, and you might say to me, okay, well, what if I just took something really, really close to -1, like -0.999, and I found the y value of that? Well, that would be all good. Let me write that number in black so that's easier to see. Well, taking a number really, really close to -1 would be a good idea, but no matter how close you get, I can always find another value that's closer to -1 than what you gave me. And then you could say, okay, well, then I'm going to find you a different number that's closer than that number. And I could find you another one that's closer. And we would go back and forth until the end of time. So even though there is this idea of a stopping point at -1, if I'm considering it to be at -1, there's technically infinitely many numbers in there. So you can never get like the highest point, the highest y value. No matter what x value you give me, I can always find another x value that will have a higher y value, even though we're actually stopping. So that's why there's no global maxes or global mins at endpoints when we don't include the endpoints. If you include the endpoints, they can be at the endpoints, but if you don't include the endpoints, they can't. So essentially, you do the same process, but if a global max or min would appear to want to be at an endpoint, you just then say there's no global whatever that one would have been. And hopefully the example, if that didn't make sense, hopefully it will make more sense when we do the example in a second. So then there's one last case, and then we'll do some examples, I promise. There's one last example of going over the real line. Oh my Lord. And this is sometimes over the entire real line, or it can also be over like half the real line. So it could be something like maybe you're going from 0 to infinity or negative infinity to 0. As long as like one of the endpoints you were looking at would actually be infinity, you're in this situation. So this one is, I don't want to say any harder, but it does take a bit more thought. So here's what you have to do. Let me pause for a second in case people are catching up. I've gotten back into the talk too fast, talk too quickly idea. Y'all can always tell me to slow down if you need to. So what we're going to do is we're going to find all of the y values for the critical points. Now I will say sometimes you don't need them, but it's good to have them in case you do need them, because sometimes you do. Now what we have to do here is we actually have to use the f prime sign chart. So the first derivative sign chart, I just don't have enough space to write first derivative. So I'll write f prime to get an idea of the shape of the graph. And I'll have to explain that a lot more in a second. So say we had a graph that looks like, no, I want to squeeze in a lot of information over here, so let me block that off. So say we have a graph of a function that looks like this. And we weren't, chopping it off anywhere. We're just considering the entire function over the whole entire real line. Well, notice that on the left and the right, it goes upwards forever. So there's never going to be a largest y value because I can always find you another value that has a larger y value attached to it because it goes up forever. But if we look at the local maxes and mins, bonk, 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 this would have a global min, right here, because that's the lowest point on the graph, but it would have no global max. Because again, it goes upwards forever in both directions, so there's never going to be a largest y value. Now, how do we figure that out without actually looking at the graph? Which you might say, well, why can't I just look at the graph? Well, because we want to figure out a non-graphical way to do it. So there's kind of three situations here, and I'm going to be squeezing a lot of information on the side here, so I'm kind of sorry that I didn't give us more space for this, but so essentially what you do is you look at the number line, just like pretend you're doing the first derivative test. You find the critical points, you plop them on the number line, you find if it's positive or negative. And what we're going to do is we're only going to care about the very leftmost interval and the very rightmost interval. So I'm going to split these up, and I'm going to put 3 dots in the middle. What I mean by those 3 dots is that I don't care what's going on in the middle of this sign chart. I'm only going to care what's going on at the ends. So it can do whatever the heck it wants in the middle, and that's what I mean by those 3 dots. So you have kind of 3 situations. Let me break this up. So either both the very left endpoint interval and the very right interval are negative, or maybe they're both positive. So the other thing, so what we're going to look at is, remember, I do my little line segments. So if you consider the line segments for these, and then consider what it would actually mean for the function at the end. So if we look at this top one, that would essentially mean that the function is going upwards forever in both directions. And in the second case, it would be going downwards forever in both directions. Okay. Dang it, I messed it up again. Doop, 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 doop. We will consider those cases in a second. I'm supposed to be considering the cases where they're different. So let me put that in red because that's the thing I just screwed up. Sorry. Always forget I gotta start with this case. Yeah, darn it. Wait a minute. No, I was right. I drew my little things wrong. Oh my lord. I was right. I'm sorry. I drew my little line segments wrong. That's what I did wrong. Decreasing, increasing. Sorry about that. So me back up. So say we're in a case where we have negative on the left and negative on the right, or positive on the left and positive on the right. So in the case of the negative negative, we'd be decreasing in that leftmost piece, which actually means it's going upwards forever on the left. And then if it's decreasing on the right as well, that means it's going downward forever on the right. Sorry about that. Or if we're in the positive positive case, if we're increasing from the left, that means we're going down forever in the left direction, and we would be going up forever in the right direction. Notice that that means it's going up in one direction forever and down forever in the other direction. There would be no global extrema at all in those cases. Because one direction you're going upwards forever, so you can never find a highest y value, and in the other direction you're going down forever, so you're never going to find a lowest value. And then the other two cases are if it's one or the other. So let's say maybe it's negative in the leftmost interval and positive in the rightmost interval. So let me draw my things correctly this time. So decreasing and then increasing. So in this case, it would be going upwards forever in both directions. If it's going up forever in both directions, there's not going to be a global max, but there can be a global min, okay? And there will be a global min. So here we would have no global max, but we do have a global min. Because we're going up forever in both directions, but that means we will have a lowest point. That's essentially, this situation is exactly this type of graph that I drew on the side. It was going upwards forever in both directions, but there was a piece in the middle where we had a global min. And then what if it was the opposite? What if it's positive in the leftmost interval and then negative in the rightmost interval? So we're increasing and then decreasing, which means we're going down forever in both directions. Here, since we're going down in both directions, we have no global min, but we do have a global max. And again, that was a lot of information to squeeze in there, so I'm sorry about that. If you're using my my layout. So essentially, if one of the endpoints, if you will, is an infinity, we have to use this idea to see if global extrema can even exist. I do want to clarify, in case anyone knows a bit more calculus than just the scope of this class. In general, this is not enough. We would have to look at a notion of a limit at the ends, but we didn't talk about limits in this class, so we can't calculate limits, so we can't do that. So the types of problems that we consider can be solved in just this fashion, but in general, you would need to talk about limits, just in case anyone thinks I'm crazy. So one last little note, and then we'll do examples. So it is possible to have multiple global extrema, global max or min. So it's okay to have multiple global maxes or global mins, because what's going to happen is they're going to occur at different x values, but have the same y value. So think of a function that looks like this. You've got these two. I tried to make them the same y value. We've got these two local mins down here, but they end up on the same y value. So they would also both be global mins. So it's not the case where you just have one global max or min. That's usually the case, but there are situations where you can have more than one global max or global min because they occur at the same y value. Okay, questions, concerns so far? I know we haven't done any examples. We're about to do some right now. Okay. So hold on like 5 more seconds in case people are writing that down. Now, I assume it's because I was writing these in hopes that we would get it done before the last exam. I don't have as many generic examples as I expected. So we're going to do the first example on here, and then we're going to kind of jump over to a blank sheet and do a couple more generic examples before moving on. So let's do that one. So we've got find the global maximum and minimum of that function on the interval -5 to 14. Excuse me. So global max and min starts out very similar to local max and min. We have to find the critical points. We have to find the derivative, set it equals 0. So what's our derivative? We've got 3x squared minus 18x minus 48. We've got to set that equal to 0, so I would suggest trying to factor this. So there's a 3 in common between all of my numbers, so I'm going to go ahead and pull it out. We have worked with this function before if it seems familiar. And then we can factor this, or you can use the quadratic formula if you just want to go ahead and set it equal to 0 and use the quadratic formula. But if we find two numbers that multiply to -16 and add to -6, we'll get -8 and +2. So this will factor into x minus 8 and x plus 2. So if we want to set that equal, well, let me do this first. This is never undefined. Let me just write that to get that out of the way. And then if we want to set the derivative equal to 0, we either have 3 equals 0, which just doesn't happen, x minus 8 equals 0, or x plus 2 equals 0. So we'll get x equals 8 and x equals -2. So now that we have the critical points, we're on a closed interval. So since we're on a closed interval, what we're going to do now is we're going to take those critical points and our end points. So we're given an interval of -5 to 14, so we also need to consider -5 and 14. And what we're going to do is we're going to take all of those numbers and plug them into the original function because we need to look at their y values. So I need to find f of -5. I need to find f of -2, I need to find f of 8, and I need to find f of 14. Oh, I also forgot that I want to show you something really quick. I'll pull that up real quick. So just in case you don't know, if you don't want to have to punch this into your calculator 4 different times, there is a kind of nice way you can make your calculator do it pretty quickly for you. So I'm going to show you that in case you don't know it. Maybe you do already know it, but just in case you don't. I'm going to pull this up really quick. So ignore that. But well, this is if you have a TI-84 or 83. If you have something different, I don't know how to do it. I could look it up. But most of you, I think, have one of these. If you didn't know, if you go to the y equals key and then you punch in your function that you want, so we want the y values for x cubed minus 9x squared minus 48x plus 52. And if you didn't know, if you hit second and then the graph key, it brings you to a table. And you can find y values pretty quickly. Now, if you need to plug in something like 200, this isn't going to be good because then you'd have to scroll all the way to 200. But for something like this, we can find it pretty easily. So what did we need? We needed -5, which this tells us is -58. We need -2, so that'll be 104. We need f of 8, so I need to scroll down a little bit. So f of 8 would be, we'll get there eventually, f of 8 will be negative 396, and f of 14 will be 360, and now I've clicked too much. Oh no. Stop. We're just gonna let it go. So 14 was 360, and I deeply this because I'm gonna have to scroll all the way back up. There we go. But if you have values that are relatively close to 0, you can use your calculator that way to get there. Yeah, Anastasia, so I pressed second, so the button all the way on the left, and then the graph key. So second graph will bring you to the table. Cool, I didn't know it could do this. Except the screen's lagging so you can't see it. Second graph. Okay. Ooh. It says I have bad network, which made people not be able to hear me earlier, but I think it's okay now. Okay. So now I got to write down those numbers that we just said. So negative 5 was negative 58, 104, negative 396, and 360. So those are our y values. So once you have your y values, now comes the easy part. What's the largest number and what's the smallest number? Well, the largest number is 360 and the smallest number is negative 396. So those are your global extrema. Done. Well, we should write the answer, but so we should say global max, not Matt, global max at 14,360. Now with these, unlike the local, you usually want the y value, which I mean you've already found anyway in the process, but make sure that you do usually state the y value in your answer. And we have a global min at 8, negative 396. That doesn't look like a 3. Questions, concerns on that? And I've got to set up the next thing I want to do. So I'll leave that up for a couple seconds while I set up. Come on, do the thing. Why aren't you working? Oh, my Lord. And technical difficulties. I don't know why this isn't working. Okay, we'll do that. We'll just do this. So again, I don't have as many generic examples as I thought because I was rushing to try to get this in for exam 2, but then we didn't make it. So what I want to do is I want to jump over here. What we're going to do is that exact same problem, but in 2 other cases that we have. So that was in a case of doing it over a closed interval. So say instead I want to do it over an open interval and then the real line. So we'll have one example that covers kind of all 3 cases before we jump into more contextual ones. But half of the work is already done for us. We just kind of have to change our answers around. So say instead I wanted to look for global and maxes and mins on negative 5 to 14, but I don't include negative 5 or 14. And I'll hold on for a second in case someone's trying to write this down on a separate sheet of paper because there's no space on your notes. But so we're going to want to do the exact same thing we just did, just not including the endpoints. So again, most of the work we've already done because this is the same problem. So we have the critical points, we have the endpoints. what we need to do now is it's a very similar process to what we just did. So we would want to find all of the y values, including the endpoints, which we already found, so I'm going to kind of speed through that. So we found that to be negative 58 and 104 and negative 396 and 360. So then here, when we were going to go and find out the largest value and the smallest value is at 8, which is okay. And the largest value would have ended up at 14. Now 14 is an endpoint, and we're not including the endpoints in this situation. So this is what I meant when I said endpoints can't win. In this case, the global max would have been at 14, but since we're on an open interval now and we're not including endpoints, there's not going to be a global max. Did I say min before? I hopefully said max. So since the global max would have been at 14, excuse me, but we can't be 14, there's not going to be a global max. So we would have a global min still at that 8 negative 396, but we would have no global max. So that's the only thing that changes between a closed interval and an open interval. You do the exact same process, but at the very end, if it's a closed interval, you just go with what your answer is. If it's an open interval, if one of your answers was going to be at an endpoint, there's just no global whatever that extrema would have been. Hopefully that makes sense. I'll wait a couple seconds before we do the last case. So we're going to do, again, the same exact function, but now we're going to look over the entire real line just so that you can get an example of a generic one over all 3 cases, and then we'll look at some contextual. So I want to do the exact same thing. So let me zoom out a little bit so I can try to keep some of the work up here. And let me maybe over the real line. So we'll say I want to look at the maxes, global maxes and mins of the same function over the entire real line. So here's the case where we have to break out that first derivative number line, kind of like our first derivative test. So we'll need half of the work we already did before. We found the derivative, we found the critical points. You would still have to do that from scratch if you were working with a different function. So we put our critical points on here. And we essentially do the first derivative test in a way. We find whether it's positive or negative in each case. So we would need our test points, so something like -3, 0, and I don't know, 10. You plug all of those values into the derivative. The derivative, because we're talking about the number line. I'm just going to go ahead and tell us what those are because I trust and believe you could slap that into your calculator. This is another situation where you could just type the function into the y = key and use the table. This would be a pretty decent one to do that for. So if we plug in 0, scroll back up. If we plug in 0, we're going to get -48. If we plug in -3, we'll get 33. And if we plug in 10, we get 72. So we have a positive, negative, positive. So if we look at what that means for the shape of the graph, we're increasing, decreasing, increasing, which means what for the ends? We're going down forever on the left, and we're going up forever on the right. So since we're going essentially in either direction in the different cases, the one side we're going down forever, the one side we're going up forever, we're going to have no global extrema at all. Now, in general, good question, Sydney. So you might be confused as to why the leftmost interval is a positive, but I'm saying it's going down forever. So if it's positive, it means I'm increasing, right? But remember that increasing goes from left to right. So I'm increasing as I move to the right, but if I'm looking at what's happening as I go to the end of the graph, that actually is looking as I go to the left. So if I'm increasing as a function, as I move to the left, I'm actually going down. So I kind of want to know what's happening when I go to the left, if the thing will catch up with me. So yeah, that's why I kind of drew those really bolded arrows at the ends, to kind of remind us that as we're looking at the actual ends of the function, the ones going down and the ones going up. In general, so this one had no global extrema. What if it could have global extrema? How would you do that? Just as a note for, later. If global extrema exists, I should put colon. Compare the y values of the local extrema. Sometimes this step, you can make it easier than that, because like in this case, well, so say you're in a case where global mins can exist. If there's only one local min, then it's just going to be at that point. Or if there's a local min but also a local max, then the local min would still be no, wait, no. My brain's exploding. I'm sorry. Yeah, no, there's no way for a local max to be higher, to be lower than a local min. Brain. Yeah, no. So, sorry, I started really freaking myself out there. So if global extrema can exist, it is going to be at one of the local extrema. So like if you know that global mins can exist and you only have one local min, then it's going to be at that local min. But if you don't want to, if you have multiple global mins, if you have multiple local mins, then you need to compare their y values to figure out which one's global. Or you can just say, I'm always going to compare all the y values of all the extrema, and that'll take care of it anyway. So that's just over the real line. If you have a situation where you can have extrema, you then just kind of have to see which one's highest and which one's lowest. Kind of in a similar way that we did the open and closed intervals. Okay, so what we've now done is we've done this function, global max on a closed interval, open interval, and the entire real line. All three cases that we could have now been done for this function. Questions, concerns on any of those while I try to get rid of my hiccups? Okay, hopefully my hiccups went away. Okay, I'm not seeing any questions, so we're going to pop back to our notes then, and I will post these problems that we just did on Blackboard. There'll be a little something. I just went back to the same thing. Over here. There we go. All right, 335. Okay. So what we're going to do now is we're going to talk about some more contextual-based ones. Now with these ones, while we are always working on an interval, it's not always explicitly stated. So sometimes we're going to have to think about what the interval we're actually working over is. And then another thing that's going to happen in this next one we're about to do is what we're going to find is we have an equation that we want to minimize, but it's going to have too many variables in it. So we're going to have a second equation that's going to help us solve that. So here's what's going to happen. We're going to look at the product of two positive numbers is 20. Find the minimum sum of one of the numbers plus times the other. So essentially reading that, I have two different equations that fall out. I have the product positive numbers is 20. So, those two numbers, let's call it x and y. So if I multiply them together, I get 20. And then the other equation is essentially we're adding one of the numbers plus 5 times the other number to get some sum. So I'm going to name it s. Now, you could have written 5x plus y. It doesn't matter which one you put the 5 on because it's generic. I just chose to make it x plus 5y. If you chose to write 5x plus y, you would technically get the same answer. It's just that our x and y values would be flip-flopped because you put the 5 on the x and I put the 5 on the y. But, okay, so here's the point. This is what we want to minimize. We want to minimize the sum, which means I would want to take a derivative of this and set it equal to 0 and find the critical points and all that jazz. I can't take the derivative of that. It has two variables in it on the left side. I know technically we usually dealt with an x on one side and a y on the other, so there's technically two variables. But what I mean is on that one side, there's two variables. There's an x and a y on the same side. I don't know how to take the derivative of that. Well, I do, but we don't know how to take the derivative of that. So what we need to do is we essentially need to get rid of one of those variables, which is where this second equation comes into play. We can essentially solve that equation for either x or y, plug it into the minimizing function, and then go about our business. So since x is by itself in the sum equation, I'm going to go ahead and solve for x. Let me also break this up. So I'm going to solve for x. You could solve for y, whatever floats your boat. But I personally just think since x is by itself, it would be easier to just replace the thing that's by itself. I also am eventually going to want to think about this as y to the negative first. So remember that that's equivalent. So essentially, I have x equals this, so I can go ahead and replace that for the x in the sum equation. So we'll have 20y to the negative first plus 5y equals s. So now I have a function that I want to minimize that only has one variable in it, so I can actually take the derivative. So we want to minimize this, so we've got to set the derivative, we've got to find all the critical points, and then we'll have to figure out what interval we're over. Because notice there's no interval stated in this problem, well, stated explicitly in this problem, so we have to kind of read between the lines and kind of figure out what the actual interval we're working over is. We'll go ahead and do that in a second. Let's go ahead and find the critical points first. So let's find the derivative. So we've got some power rules going on. So bring the power down so we get negative 20 y to the negative second, negative 1 minus 1, plus the derivative of 5y, which is 5. Once I find the derivative, I want to set it equal to 0. And I'm going to rewrite it as this now. I'm going to set it equal to 0. I'm even going to come up here at this point because I'm going to want to write something down here. I'll do that down in that space. So if we add the 20 over y squared over to the other side, and this is why I decided to rewrite it as over y squared, because if you were to write this as 20y to the negative second, you might not realize the algebra that you want to do next. Or maybe rewrite it as 20y to the negative second, and then maybe you would realize that I don't know what to do algebraically. Let me rewrite this as 20 over y squared. Because what you want to do now is you want to multiply both sides by y squared. I'm going to run out of space if I'm not careful. I'm pretty much already running out of space. Let me erase that and let me save space over there. Divide both sides by 5. Let me slow down a second. I'm sorry. Square root both sides. Seriously, y'all. If I start going too fast, just yell at me. Now, I only need to care about the positive too, because we're told positive numbers in the original statement of the problem. So in the original problem, it says the product of two positive numbers. So even though square rooting would get me a positive and a negative, I only care about the positive case because we're only working with positive numbers. Now, technically, This derivative has a denominator if I write it as negative 20 over y squared. So we would need to consider undefined. Whenever you have a denominator, you set that sucker equal to 0, which would get us y equals 0. 0 is not considered to be a positive or a negative number, really, so we don't care about that either. If we did care, we would just have to look at its y value. Well, I should be careful with y value. Its value in the original function. So you know how in the one we just did, we had to find critical points and then plug them into the original function? So if we were caring about 0 here, we would need to plug that into the original function. That's the only thing that changes. But we don't need to care about it because it's not a positive number. Question so far. Okay, so we have the critical points, but now we don't know what to do with them because we don't know what interval we're working over. Do we compare them in the original function? Do we have to do a number line? What are we working with here? So what I'm going to do is I'm going to come back to the left side, or else I'm going to run out of space because I want to leave that right side for the answer. So I'm going to come back over to the left side really quick. And so we're considering y values. So let me look at what, interval I'm on in terms of my y values. What's the smallest y could be? Well, essentially it can be as close to 0 as you want, but not really 0 because 0 is not positive. So we can get as close to 0 as we want, but then we can go as large as we want. There's no like cap here, since all we're going off of is the fact that they have to be a positive number. So that's kind of the piece that gives us our interval, is the fact that they say two positive numbers, which tells us that our interval is essentially 0 to infinity. So it doesn't state it explicitly, but the context in there kind of told us that that's the interval we're working on. So note that one of our endpoints is an infinity, which is in the unfortunate case of where we have to actually find a number line. So we'll have to find a first derivative number line here. So our critical point was 2. The only other extra thing I'm going to do here is, since we have an interval that stops at 0, I'm going to go ahead and cut this off at 0. So I'm not going to use any negative numbers because that might actually throw some things off if I take things that are outside of my interval. So I'll choose 1, and I don't know, I'm going to do obnoxious. I'm going to choose 100. So we got to find whether it's positive or negative in those two cases. So we're plugging them into the derivative. Let me remind us where our derivative is. Either one of these two forms, whichever floats your boat. If I plug in 1, we're going to get negative 20 over 1 squared, which is negative 20 plus 5. That'll give us a negative number. It'll be negative 15. If I plug in 100, we'll get negative 20 over 1 over 10,000, which is a small negative number. Plus 5 will give us a positive number. You can figure out what the actual number is, but it'll turn out to be positive. Negative 20 divided by 10,000 is smaller than 5. So essentially that means that our function has the shape where we're increasing and then decreasing. So at the end points, maybe I should not say end points, but towards the end of the function, we're going down forever in both directions. So since we're going down, that's wrong. I drew my things backwards. Where is my brain today? We're decreasing and increasing. So we're going up forever in both directions. I'm really sorry about that. My brain's apparently not existent today. I started to panic a little bit because that was going to tell me there was a max and I was trying to find a min. So sorry about that. So we're decreasing, increasing, which means that we can have a global min, which is good because we're asked to find a min. So the fact that a global min can exist is good. So we'll have a global min at x equals 2. No, it was a y value. Sorry, I'm so used to just jumping to the answer. So I can just immediately say that it's 2 because that was the only local extrema I had. If I had more local extrema, I would have to consider all of them and find which one has the lowest y value. But since that was the only local min we had there, that's going to be the global min. Now, one last thing with ones like these. is you want to go back to the very original statement of the problem and figure out what they actually asked you for. The question says, find the minimum sum of one of the numbers plus 5 times the other. So they want to know the actual sum value. So they don't want y equals 2, they want the actual sum. So the first thing I would probably need to find is what x is. Well, I don't really need it, but let's go ahead and find out what x is. How the heck am I going to find out what x is? Well, I know what x is in terms of y. So I can use this relationship from way back in the very beginning to say, okay, well, if y is 2, we can say, and x equals 10, which is coming from 20 over 2. For a sum of 10 plus 5 times 2 equals 20. So the 20 is the thing they actually cared about. Stating the x and y are good, but technically the answer they wanted is that 20. Let me get rid of the circles around the derivative value, but I'll leave everything else. Questions, concerns about that? So the main difference here is that the function that we wanted to minimize had too many variables to start, so we had to use a second equation to get rid of one of them. But after that, the process was the same for that original one that we just did before. Yeah, so Ben, how did I get that x value? So way back in the very beginning of the question, we found that x was equal to 20 over y. So once I found that y equals 2, I plug it in there, get 20 divided by 2 equals x, so x would be 10. So that's how I found x. I took the y value that I found, I put it back in that relationship that I had from the very, very beginning of the question, and found my x value. How did I find the sum? So I probably should have been a bit more about that, Anastasia. So remember that the original sum is this x plus 5y. So that's the original sum once it catches up with me. Well, one of it's caught up. So the original sum equation was x plus 5y. So if I know that y is 2 and x is 10, I plug those in, I get 10 plus 5 times 2. So 10 plus 10 is 20. That's where I got that 20 from. Does that make sense, Anastasia? Cool. So yeah, sorry, I was going back to a bunch of the stuff from the beginning and not quite being super explicit about it. And now my nose itches. Goodness gracious. Any more questions about that one? All right, we've got 15 minutes. I think I'm going to try to squeeze in one more. Should be able to do it in 15 minutes. So this next one is a very popular one. Pretty much any calculus class you'll ever take will do an example like this. Maybe not any calculus class, but also I'm pretty sure there's one of these on your homework. I also think there's one of the ones like the one we just did on your homework. But anyway. So we have 800 feet of fencing to fence off some land with a river on one side. What is the largest area fence off? So first off, let me kind of draw what's going on here. So there's my wonderful river. Look at that. It's so pretty. And we're essentially fencing off some area. And we don't need to fence off the area that's attached to the river. Like say you're just putting some chickens in there and the chickens aren't going to swim away. I don't know. Do chickens swim in a river? Anyway, let's pretend the chickens aren't going to go in the river. So we don't need to fence off the side with the river. So let's go ahead and give these names, give these sides some names. So we'll call the shortest, well, the shorter side's in my drawing, X, and then the other side, Y. So what are we asked for? We're asked for the largest area. So we would really love to find out what X times Y is, and we'd really like to maximize that. Where am I getting that from? So here, gotta remember back to geometry a little bit. What's the area of a rectangle? Length times width. So X times Y is going to give me my area. So I want to maximize that function. That function has too many variables. So we have to get rid of one of those variables using a different function. What other function do we have? Well, we have this piece of information that we have 800 feet of fencing. And if we're trying to get the largest area, we can pretty much assume that we have to use all the fencing because we want the largest area, so you probably want to use it all. So if we have 800 feet of fencing, that would mean that essentially the perimeter of this kind of rectangle, I know it doesn't have a fourth side, but we essentially have 2x plus y, which would have to be equal to 800 because that's the amount of fencing they have. So now I have this second equation where I can solve for one of those two variables and replace it in my area function. So you get to solve for x or y, whichever one makes you happier. Y makes me happier because it doesn't have another number attached to it, and the algebra is going to be easier. So I would personally solve for y by subtracting 2x from both sides. Once you have it solved for, so we are going to want to remember this, so let me box it to kind of remember that we're going to come back to this later. But we're going to go ahead and put that y into the area equation, which is the thing we actually want to maximize. So now the equation we want to maximize only has one variable, so we can go ahead and take the derivative. Now, as it's written, I would have to do a product rule, which is meh. So why don't I go ahead and distribute that x? I don't have to do a product rule anymore. So let's go ahead and distribute that x. And now it's just going to be a bunch of power rules that we can take the derivative of. So needed to take one equation, solve it for one thing to replace it in the other equation because we want to take the derivative, set it equal to 0, find critical points, and I can't take the derivative of something that has more than one variable in it. So I want to take the derivative of this. So we have 800 minus 4x. I want to find the critical points. So first of all, this is never undefined. Just make that note. There's no denominators here. But then we will want to set it equal to 0. Add 4 to both sides. Divide both sides by 4. You get 200. So we found a critical point. So at this point with global max and min problems, we need to know what type of interval we're working over. So again, it's not explicitly stated here, so we're going to have to think about it a little bit. So let me come off to the side on the left here so that I save myself space for the answer on the right. So we're working in terms of x values right now. So if you think about this, what is the smallest x value could be here? What's the smallest x could be? Now, while you couldn't be equal to it, because then you wouldn't really have an area, you could almost be 0. Like you could have that x value only be like a half of an inch, half of a foot, excuse me. You would have a very, skinny strip of land fenced off, but you could do it. So technically the smallest value here could be really close to 0. We're not going to say it's equal to 0 because then again, you don't actually have an area that you fence off if you don't have a side. So we need to at least have the tiniest bit of substance. So we need it to be not equal to 0, but it could technically be really close to 0 if we wanted to, for some reason, just fence off a very skinny strip of land and say, haha, I fenced off your river. So what's the largest x could be? There's a couple ways you could think about this. I think the easiest way to think about it is the largest x value is going to come when y is smallest. So the smaller y value is, the smaller y is, the larger x is. So what's the smallest y could be? Well, kind of 0. Well, if y is kind of 0, I'll put it in quotes. Well, if y is 0, then we would have 2x plus 0 equals 800 from the function above. So 2x equals 800, so x would be 400. So the largest x can be here is essentially obnoxiously close to 400. The other way to think about it is if you want to use essentially all the fencing for the x values and only leave a very small amount for y, you still have two sides that need the x value. So you essentially need to split that 800 feet into two pieces. That's the other way to kind of think about it. So the largest x value we could have is essentially 400, but not quite equal to 400 because, again, you actually have to have some substance. So you could have some very skinny strip coming out from the river and just say, haha, I've made a weird fence. But you could technically do it. So what we found now is we found that a purely open interval, but there's no infinity or negative infinity, so we don't need a number line. So what we do now is we just take our endpoints, 0 and 400, and our critical point, 200, plug them into the function that we wanted to maximize or minimize, the original one, and compare the values of the original function. Now, the function we're trying to maximize or minimize is the area. Now, the original one was x times y, but you can use the other version that's just in terms of the one variable. You could also use the x times y if you want to find y in each situation, but we're going to go ahead and use this one. So essentially we need to find three things. We need to find if x, we were working with x's. If x is 0, what is a? If x is 200, what is a? And if x is 400, what is a? Let me actually move a over a little bit. So if x is 0, we have 800 times 0 minus 2 times 0 squared, which is going to be 0. If we plug in 200, A is going to end up being 80,000. And if we plug in 400, we get 0 again. We wanted the maximum, the largest area. So which one of those three numbers is largest? Hopefully that's pretty obviously 80,000. So we've essentially found our answer. We just need to actually write the answer now. So what did they ask for? They asked for the largest area. So technically the only thing we need to say is that 80,000. So the largest area is 80,000 feet squared. I'm going to go ahead and list the x and y value though. So x was 200. And if we wanted our y value, this is where we have to go back to that kind of relationship that I boxed way back when, because I said we were going to need it eventually. So if I plug 200 into that, we have 800 minus 2 times 200, which will give us that y is 400. So we didn't need the x and y value because they just asked for the largest area, but I usually like to list them just in case, especially on these examples. I like to go ahead and just list them in case. But that's where you need to just go back to the original statement of the problem, figure out what they actually asked you for, and make sure that's what you're giving them. So let me babble through this one more time. We wanted to maximize the area function. It had one too many variables in it, so we needed to use this other equation that we got from the context of the problem to be able to replace one of those variables. Once we replaced it, we could take the derivative and find all of our critical points. Once we found the critical points, we needed to figure out what kind of interval we were over, so we thought about it a little bit in terms of the context of the problem. Found out we were on a purely open interval. So in an open interval case, that's where you want to compare the original function values at all of the critical points and the endpoints. So that's what we did on the right with the x equals 0, x equals 200, x equals 400. And then you wanted the maximum, so you just pick the largest number. One last thing I want to babble about really quick is, say they were asking for the minimum area, which would be a little silly, but say they were asking for the minimum area. Note how at 0 and 400 it's both 0, which would be the minimum, but we're on an open interval, so there is technically no minimum area here. Because again, since we're not actually allowing it to be equal to 0 or equal to 400, because then you wouldn't actually have any area, you would just have a strip of fence. Since we are not allowed to actually be those endpoints, there's no minimum because you can always get smaller. But there is a maximum, and it was 80,000. We're 4 minutes early, but that's not enough time to do anything else, so we're done. If you have any questions, feel free to stick around. Oh, let me talk about your quiz. Your quiz on Thursday. So, well, one thing, we have technically 2 more to go through in these notes. So we will finish those 2 on Thursday before starting chapter 5. But your quiz on Thursday, since it's the only thing we talked about, is going to be this idea, but it's going to be more like example 5 and possibly like the one we did over in my OneNote where it was the open interval or the real line. So I'm not saying that it's only going to be a closed interval, but it's not going to be one of these where you have 2 functions. So you are going to want to be able to, it follows a similar process to what we just did because we do the generic process in example 6 and 7. But what I'm saying is on your quiz, it will just be based off of 1 function that you have to maximize or minimize. You won't have to find a second function to manipulate. And the last 2 that we're going over on Thursday, well, example 8's a little weird, but example 5, problem 5, I guess, only deals with 1 function. So yes, I will upload those examples that I did on that scratch paper. Those will be up on Blackboard with the rest of it. Don't worry about that. I will get that up for you. But that's what your quiz will be on. It will be on finding global maxes and mins, but just in terms of just 1 function. You won't have to manipulate 2 of them like we just did in 6 and 7. So now, if you have any questions, feel free to stick around. Otherwise, have a good day, and I'll see you on Thursday. And yeah, I'm going to stop recording now.